Hello, on behalf of Renzi at the University of North Carolina at Chapel Hill, and of University of Southern California, ISI, and of University of Missouri College of Engineering, and of University of Massachusetts Electrical and Computer Engineering, my name is Eric Lyons, and I'm here to talk about FlyNet, a dynamic data-driven sensor net for scalable small aircraft operations. You can't hardly imagine the future without all sorts of flying cars zipping around. It all seems so simple on the Jetsons, but it never seemed to rain. They must have lived in Southern California. Yeah, I'm thinking definitely had to be Southern California. The truth is, no matter where it is, it's going to be a complex operation. Small aircraft have to deal with many things, including aerial hazards, weather, flocks of birds, known air traffic, and unknown air traffic. They have to consider energy consumption, battery and fuel usage. They have flight registration and communications protocols to follow, entering controlled airspaces, talking to the FAA on the ground, communicating with other local fleet operators, and also communicating within your own fleet. There's noise and emissions considerations. They have vehicle health and monitoring systems, which are crucial to safety, and mission-specific considerations such as streaming video, bandwidth loss, GPS signal loss, etc. FlyNet leverages the expertise of multiple institutions to start addressing these challenges within the academic environment. We hope to provide innovative approaches for the burgeoning aviation industry. Small aviation could be $1 trillion industry in a decade. We want to create an architecture for reproducible experiments. We want to simplify resource management and optimize scientific workflows for researchers in this field. By leveraging highly configurable infrastructure such as Exogeny and Fabric to determine where to locate processing in the network, to demonstrate specific use cases for small aircraft with real-world data. I'm going to go over our initial use case, flight path routing for delivery drone operations in the presence of weather. Your first task is to enter pickup and drop-off locations. You can see in the image on the right our Google Maps-based web app, where you can enter these into text boxes. And a line is created between these 2 points, and you can see that in this case, the line intersects with these green polygons that represent abstractions of weather. When you click on the $sign button, you're going to create this GeoJSON formatted structure here, similar to what's shown on the left-hand side. Let me go through that quickly. It contains an event name, a pickup and drop-off time, and also a series of weather products and associated parameters. These represent areas that you want to avoid. For example, rain rate CASA. It has a threshold of 1 and a threshold units of inches per hour, a distance of 3 and a distance units of kilometers. So you're saying you want to avoid areas where it's raining greater than 1 inch per hour with at least a 3-kilometer buffer. And you can enter these for different weather types and also different sources. For example, forecast sources you may want to give more buffer to because of the inherent uncertainty in forecasts compared to the uncertainty associated with actual observations. Here's some context for our weather system. Back in 2013, the University of Massachusetts Amherst began to deploy a network of 7 operational high-resolution Doppler weather radars across the Dallas-Fort Worth Metroplex in North Texas. Data from these radars is sent to the NOAA Radar Operations Center and also to dynamically provisioned compute centers, where various weather workflows fuse this together to create useful meteorological products for decision-making. In addition, we take in other types of sensors, including weather station data, hail sensors, lightning sensors, NEXRAD radar, MRMS precipitation, and meteorological models, including the University of Oklahoma ARPS model, NDFD, the National Digital Forecast Database, and the HRRR model, which are incorporated to expand beyond North Texas and also to improve understanding of current and forecast atmospheric conditions, which is important for flight planning. It takes a tremendous amount of compute to process all this data. At times, it's not necessary to process all of it. For example, if it's not raining and no rain is expected, you don't need to run hail detection algorithms. At other times, the load associated with processing it all spikes when widespread weather is occurring. We use the Mobius cloud provisioning tool created at Renzi to instantiate weather workflows on the cloud based on their resource requirements. Mobius creates private layer 2 networks and uses virtual STX to prioritize bandwidth to these based on their input requirements and their utility to users at the given time. The image on the right shows an example of different weather workflows that are created with Mobius along with the bandwidth that is provisioned for them. This is an example of an architecture that Mobius would create for processing weather workflows. Let me start on the top right-hand side of the image, workflow node at UNT. This is a dedicated computer located at the University of North Texas. This is where data arrives from the NOAA Southern Region headquarters, live, radar, and other types of weather sensor data. In the meantime, Mobius is instantiating a slice at the University of Massachusetts on Exogeny. Pegasus will be running here. This will schedule efficiently our jobs associated with the workflow. And Mobius also schedules another slice where virtual STX will be running to control the bandwidth to the actual worker nodes. Finally, Mobius will create 4 worker nodes located at the University of Texas Austin TAC, the Texas Advanced Compute Center. These are high-end worker nodes, and also a shared storage drive for both containerized executables and also any shared data. For more information, please see Papadimitriou et al. At the Supercomputing 2020 Indus Workshop. In addition to actually creating the network level products from the single sensor data, the weather workflows can also extract particular levels of interest and send them into our obstacle database as the basis for flight path routing. For example, in the image on the center, which is the background image is forecast reflectivity, we've picked a particular reflectivity level, which we believe is a proxy for rainfall that we want to avoid, and created closed concave polygons using an enhanced marching squares-based contouring algorithm. Similarly, on the image on the lower right, which is a hydrometeor classification image, the orange polygon represents an area of hail where the green represents areas of rain. The red polygons come from a wind image, which is not shown, but these represent areas of high winds that an aircraft would also want to avoid. Finally, the algorithms can create custom data extractions over infrastructure to pinpoint risk and to inform disaster relief efforts, including drone survey missions. All right, so you've seen a little bit how the weather workflows are working, and you've also seen the Google Maps-based web app to generate flight requests. So let me step back to that part for a minute. When you first make a flight request, it's entered into our flight database. It's a MySQL database. Mobius and Pegasus are reading the contents of the database, and they're extracting the flight weather parameters, both in terms of the type of weather data of interest and also the thresholds of interest. And they make a determination whether the weather workflows are appropriately running on the cloud or if they're running at all. For example, if a flight is requesting hail information, there's no hail workflow running in the cloud, Mobius will actually go ahead and instantiate a hail workflow. Or conversely, if no flights are currently interested in hail and a hail workflow is running, it can release those resources back to the cloud. Moreover, it can make determinants of priority about how many flights are interested in particular kinds of weather and prioritize bandwidth with virtual SDX appropriately. In addition, it looks at the total amount of load in the database and makes a determination of how many number of flight routing and flight simulation workers are going to be necessary and assigns those tasks to those workers. Meanwhile, when that initial request is made, it's sent to RabbitMQ, the name of the event. Once the flight routing and flight simulation tasks are assigned, they begin reading from the job queue the name of the event. And because everything is asynchronous and the flights could be constantly being updated, they query the flight database for that particular named event to get the latest information and begin their tasks. In the case of flight routing, it re-extracts the weather contours associated makes a custom query to the obstacle database and is returned those set of contours. For flight simulation, it's taking the location of the flight and looking at the elapsed time and the flight speed, and it's simulating the advancement of flight along that path. And in both the routing case and the flight simulation case, once they're done, they resubmit jobs back to the RabbitMQ job queue with a certain delay, because we're going to keep running flight routing and flight simulation over the course of the entire path. This is how the flight path algorithm actually works. The latest weather concave polygons are queried from the obstacle database based on the weather parameters. Safety and uncertainty buffers are added on a per feature basis, and then the polygons are merged and regenerated into a master obstacle course. A graph is created using the convex hull points of the master obstacle course. We use the Graham algorithm to generate the convex hull points. This is important to reduce our search space because, unlike with roadways, where intersections are traditionally used to generate graph points, in the case of aviation, you could have virtually infinite vertices in the search space. Ultimately, we use a modified A-star algorithm to generate the shortest path from the resultant graph. Results are posted back into the flight database along with a new end time, estimate, distance, and cost. Let me first discuss this image on the right. This is another simulated path request. Once again, the green polygons represent extractions of weather data. You see it looks like 3 almost identical polygons overlaid on top of each other with an offset. And in fact, that's exactly what it is. And that's because these are forecasts. In the foreground, the more opaque image is a 5-minute abstraction of where we believe it's going to be raining. And behind that, a 10-minute, and behind that, a 15-minute. So you see that in general, we expect the motion of this weather system to be roughly north-northeast over time. And every minute, we're going to regenerate where our predictions of this weather is going to be. But once again, as I mentioned earlier, forecasts are highly uncertain. And so this will not be continuous as though it were really observed in time, again, because these are predictions, so they can have the potential to jump around here and there. So once the flight starts, we're going to constantly be rerouting on our best estimates of where the weather is going to be. And the flight simulator will advance a flight in reasonably realistic ways based on their flight speed and their path. Routing is going to keep reoccurring on an ongoing recursive basis over time. But you'll see once again that the estimates of where the precipitation is actually going to be are semi-unstable. Now, even in general, if operations are going to want to rely on longer-term forecasts for strategic decision making, in other words, they may say, we want 2 hours of notice to make a call on whether we can actually execute on this flight. At the time of the actual flight, they'll still have to consider developing and perhaps unexpected weather and be able to navigate it. That's going to be crucial for safety. Forecasts are only so good, and if you take even small chances of rain and think, well, the flight's probably okay to go, and then something unexpected pops up, you're going to have to be able to navigate it. Here's an example of our flight in progress. You see that the route is calculated to the south, and you can see the plane starting to fly that flight. In the meantime, the weather is advecting north as expected, and the flight path is constantly being rerun and getting shorter. The flight trajectory proceeds toward its end location as the weather advances. And at times, the flight has to take a slight deviation to maintain the appropriate safety buffer. But ultimately, the flight that ended up occurring is substantially shorter than the original flight estimate shown at the beginning. Once this will start over again. We believe this recursive method will be crucial to always be updating the flight with the latest information. However, there are complications here as well. Because the flight always wants to be changing, when you're talking about fleet operations, you have to consider that it'll be hard to make pre-existing assumptions of where given flights are going to be, which is going to require rapid communication with the latest updates and routing to maintain safe distances away from other aircraft that are doing the same thing and often routing around the same weather that you are. Scalability is a primary concern of FlyNet, and our system is well set up to handle it. Mobius can keep acquiring resources as needed, and Pegasus can efficiently schedule both routing and simulation jobs on these worker nodes as the load grows. And the Google Maps-based interface has an option to generate an arbitrary number of requests. This is going to be really important for traffic analysis and various other aspects that will complicate the problem. Mobius also ties in with Prometheus to do resource monitoring on the cloud. This is all just the tip of the iceberg for FlyNet, which is a new project. Our simulation so far uses actual observed weather data with a vast case archive from the CASA radar network. And it works 100% in real time and keeps up as the live weather evolves. And it's highly scalable, and we can grow the number of requests and still keep up. But I think we can all agree that vast work remains. For example, we have to take into account, how do headwinds and tailwinds and crosswinds affect flights in the flight simulator? How are we going to handle the fleet traffic and maintain distance with flights constantly rerouting, and also especially rerouting around the same weather? How do we simulate vehicle degradation as batteries decrease, or if communication should be lost? And how do we handle unexpected weather causing diversions, either pre-flight or in-flight delays? For example, should the aircraft hover? Should it return to base? Should it seek to land elsewhere? These are hard questions to answer that we hope FlyNet will help address. We want to send a special thanks to the National Science Foundation for their support for FlyNet, and for the many academic clouds that they have contributed to that we make use of, including Exogeny, Chameleon, Fabric, and the Mass Open Cloud Testbed. Thank you, NSF. And also thank you to our many partners and contributors and advisors for this effort. Thank you very much.